training session number 9, ACPI, PSCI, and UEFI to boot. Sorry for the slight late start, but the previous presenter, damn him, overran. So I'm Bill Fletcher from the Linaro field organization. The field organization exists within Linaro primarily to make sure that members get value from their Linaro membership. We do that in a number of ways. For instance, we're a contact point for new requests or new inquiries from members about particular things that Linaro could do. We field support, we field bugs, we have premium services. And also, through a strand like this, we talk to members about technologies which are available through Linaro or as a result of collaborations that Linaro is involved in. So my previous talk was about Lava, which is obviously a Linaro technology. The elements that make up this talk are obviously a very big collaborative effort, so I don't want anybody to feel that I am fronting this as a Linaro branded thing. One of the reasons why this little talk came about, and I'm aware that there are kind of the great and the good of UEFI, ACPI and PSCI in the room, so please manage your expectations. Was that quite a lot of friends and colleagues that I spoke to would say things like, oh yeah, ACPI, yeah, I'll get around to looking at that at some point, but not right now. It's not really kind of made it up on their to-do lists. So I did, this is a consumer's view. It's an introductory look. It's a tutorial for someone new to the technology, and so or maybe one or two of you are quite deep into some of the elements of this. So obviously, if I get a question, I may look at you. And also, I ask your forgiveness if I use particular terminology that you may consider. I know. I'm going to have a few bruises by the end of this. Yeah. But what I do is I take a platform, qemu, I take a piece of firmware called UEFI and the kernel to set up something basic with ACPI. And I just talk a little bit about that in the context of a system based on what's in 4.1. And again, this is very much from an outside in, from a consumer's view, rather than a lot of the presentations that Connect are very much inside out, hardcore developer stuff. I have a little demo running in a virtual machine on QEMU, and I have a little bit of, to which I am indebted to various colleagues providing me a few kind of threads of what's new, just so that I end on a kind of, a kind of upwards inflection at the end of the presentation. So caveats. This is not an exhaustive tutorial on ACPI. One, because I couldn't do it, and two, because you wouldn't want to sit through it, I would hope. So if anybody had that expectation, then you could leave now, and we will part as friends. It's also not a reference implementation for PSCI. I know what a reference implementation for PSCI is, because as I read it, and I'm deliberately using QEMU, so be aware of that. And I know that there are a lot of friends and colleagues who are like, why should I use ACPI instead of device trees, or why to favor UEFI instead of U-boot, and I don't engage with those questions. And there are probably a lot of other things that this presentation is not, but those are the main ones. But I have a little bit of kind of preliminary stuff, put everybody on the same page. ACPI, well, I put one page, then I have another page on ACPI, so it's a two-pager. The Advanced Configuration and Power Interface specification, currently at 6.0. It's on uefi.org because I think in 2013 they transferred the spec from the ACPI developers to UEFI. Industry standard interfaces enabling OS-directed configuration, power management, and thermal management since 1996. And I added the since 1996 because it's been around for a long time. In fact, if it was a bottle of scotch, it would be really great. That was the only joke that I could come up with for us. Actually, I have another one. See if you notice it. It's important, and this is a quote from the kernel documentation, because hardware and OS vendors have already worked out the mechanisms for supporting a general purpose computing ecosystem. Those are Graham Gregory's words, not mine. And that means it's, you all know, it's not negotiable in the enterprise environment. And there are three main elements to it. There are tables, there are drivers, and there are registers, or register blocks. And there's an interpreted element. The actual tables are written in something called ACPI machine language, which is stored in the tables. So if you want to read the tables, you have to use a little tool to disassemble the bike. And first of all, this is a homage to another picture on another slide, which somehow got corrupted, so I redrew it. So credit to the person who drew this originally. But ACPI looks like a chain of tables. So you find an initial pointer, which points you to a table called the extended system description table, which is basically a list of other tables. And then that gives you a pointer to a table which tells you pretty much about ACPI, called the fixed ACPI description table, which then jumps you off to a very interesting table, I think. A good place to start if you wanted to look at an ACPI table and be drawn in by the interest and complexity, then maybe the differentiated system description table will be an interesting one. Because the differentiated system description table has a list of devices, and for each device calls out the interrupts, registers, driver entry points, even methods to find out what interrupt controllers might be local to that device. A lot of stuff in there. And so this is an example of how you get to there. And there are also other tables that I'll talk about as I go on. But that's kind of enough for now. Are there any questions on that very thumbnail sketch of ACPI? First of all, how many of you are kind of deeply involved in ACPI right now? Okay, well, hopefully anybody else who didn't put their hand up, this is maybe a starting point. I'm aware of lots of ARM people around, maybe some in this room. So Power State Coordination Interface, PSCI, it's an ARM standard. So ACPI is an industry standard. PSCI is an ARM standard. And it's the official or only way for power management on ARM64. It's a low-level interface for power management. It lives, well, I dug into, to the best of my limited abilities, I dug into the code, and it lives quite a long way down under CPU ops, under CPU idle, and the CPU governors. It's not really something that you can play with interactively. And there's a list of the things that it covers. Idle management, addition and removal of cores, booting secondary cores, core migration, system shutdown, and reset. And it's not specifically just for ACPI. It has bindings for both ACPI and device stream. Now, I do have to stop at this point and ask if anybody at ARM wants to say anything about PSCI or correct anything I've said. No? Okay, that's cool. So booting. So this was my little conceptual boot model for booting ACPI. So I have a root system pointer, which was the little yellow box at the corner of my chain of trees, chain of tables. And so if I'm booting, then I should find that pointer. I should somehow use that pointer to load the tables. The tables will tell me about PSCI, and then I have an ACPI-aware system. And so, but if I took an ACPI-aware platform, like qemu with the patches for ACPI, and I take a kernel and I build it for ACPI, or ACPI equals force in the command line and I boot it. It doesn't know anything about ACPI, which was a disappointment to me. And I discovered that actually I have to have a piece of firmware. I know, I have to have a piece of firmware which conforms to the UEFI standard, but which is built from the EDK2 code base. I'm looking at Leif for every sentence right now to see if he's happy with the words that I am using. But those were okay, I think. Thank you, yeah. And there's a quote which lightened my darkness, which I'm going to read verbatim. And if the person in the room who actually wrote this is here, he can maybe make himself known. Which is the generic interface for discovering ACPI tables is to boot as an EFI application, and then to query the tables from UEFI. That's the interface others are likely to follow, and ACPI without UEFI is unlikely to be of much use to anyone else. Okay. Anybody know who said that? Well, you can Google it afterwards. I didn't make it up. But also you will find in the kernel documentation for ACPI for ARM basically the same statement, which is that if you want to build a system with ACPI, you're going to have to build that system with a UEFI firmware boots. I did look at what kind of goes on around the EFI boot, and obviously there's for those of you, I'm talking to two different audiences here, so bear with me. People who are new to this and people who know all this stuff inside out. And so people who know this stuff inside out, if you could kind of do some mail, that would be great whilst I do my own halting explanation of this. Which is that the EFI stub loader makes the Linux kernel image into a UEFI application. And the way that the kernel finds out about how to access UEFI is by a device tree which is kind of created on the fly by that EFI stub, and which I thought was kind of cool, actually. And you can find some more about this in the LEG wiki, and actually, if you dig down underneath firmware lib stub, then there's some code that does this, and a trail of breadcrumbs leading to EFI.h. Okay, you can look up from your mail now, and if you should just shake your head sadly at me if there are any kind of quirks in it.
I'll make a comment.
Please.
Which is DP equals is basically a development feature.
Right.
Ecosystem got way too used to just, I built my kernel and I built my device tree with it, and you always have to have the right kernel with the right
Yeah.
In a system that uses firmware, you are more likely to actually have, even if you're using a device tree for hardware description, to just have that already registered within your UI. You actually end up discovering it the same way you discover where ACPI designs.
Right.
So you don't need to try it at all.
So I could take this out, actually.
Basically.
That would make it. Yes. Okay. Thank you.
If anything, it should be strongly discouraged.
Okay. Well, you heard it here. Thank you. So I actually based this this little I was going to call it an odyssey, but it's more of an excursion or a day trip, based on what was actually upstreamed into 4.1, but actually used it in the LEG kernel with the patches that were there just before it was upstream. So what functionality does this give you? And it's basic support to run ACPI on ARM64. So SMP and GIC v2 support in the table which defines the interrupt controller. the announcement of PSCI support in the table that tells you about ACPI, ARM timer support in the generic timer description, and some documentation on ACPI in the kernel documentation. Now, I actually took that pretty much as a verbatim quote, so hopefully that doesn't under or oversell anything. But it is, I think the first word is probably the best descriptive one. It is quite basic. Why talk about this now? Why is it interesting? Why do I think it's interesting? The 5.1 spec supported ARM specifically for the first time this year. ACPI on ARM is a major and continuing LEG collaboration between ARM and Linaro. And another quote from the documentation, there's no longer any reason to feel that ACPI only belongs to Windows or that Linux is in any way secondary to Microsoft in this arena. So that's a reason to get started, Pete. So I built a little demo using QEMU. All my QEMU skills come from Alex's blog. I built UEFI. All my UEFI skills come from Leif's blog. And I went and got the ISL compiler myself. And it lets you boot UEFI as a guest, boot Linux image from UEFI, confirm ACPI is enabled, dump and read the tables, and if you like, you can dig down into QEMU and write your own messages and see them in your own ACPI tables if you wanted. So, in the running system, so I mentioned that when UEFI boots, or maybe I didn't mention, maybe I'll just go back a few slides. I didn't mention that as well as getting the root system description pointer, so the start of that chain of tables, there's a platform-specific function within the EDK2 firmware to load the tables from the platform, in this case QEMU. Install QEMU firmware configuration tables. Is that the right thing? Well, it gets called and it loads 5 tables, so that's the evidence that I think this is the right place. So in my boot, here it says that function being called and installed 5 tables. So this is UEFI loader reading the ACPI table. And you're laughing at that point, so you tell me why. Is that okay? Okay, that's all right. As long as they're only going to earn me a slap from you, that's fine. Or one of your henchmen. And I also happen to notice that PCI happens first and then ACPI happens afterwards. So I guess it needs to figure out PCI before it figures out the ACPI configuration. And then booting my system, so booting with ACPI force from the UEFI shell, having an ACPI entry in proc, and then having my 5 tables in sys firmware ACPI tables, just to show that it's there. Some more information on the tables. That's pretty much basically saying the tables report what I said was the functionality in the 5.1 standard and the 4.1 kernel. And they're all...
that third point is slightly misleading.
What's that?
Way to access PSCI status HPC is misleading. The table describes whether it's HPC or SMC, whereas that makes it sound like it's always HPC.
I understand your point. So in my particular table, which is here, it's HPC, but you're right. And because I don't have a secure monitor in this system, yes. Yeah, I get your point. Maybe it could be ordered a bit better to say, this is what my example does, And in this case, it says HVC, but yes, you're right. It could be ordered slightly. So if we just leap into the tables, this was the one that I said was the most interesting, the DSDT, which has CPUs. Here's a COM device, and I mentioned that it has things like memory locations and interrupts, and also commands, driver entry points. This is the table that tells you about PSCI, that PSCI is present, and as you said, in this case it's HEVC, but the calling convention can either be HVC for having a hypervisor, or QMU, or secure monitor call if you've got ARM-trusted firmware. Not very easy to read the slides on, put the tables on slides, so I actually have a link to just the dumps of tables, in case people wanted to look at ACPI tables for a simple system. This is my favorite table, the multiple APIC description table. An APIC being an advanced programmable interrupt controller. Does anyone know what an 8259 is? It's an interrupt controller. An advanced programmable interrupt controller is anything more advanced than an 8259, is what I read. The analogy that I thought of here was modern jazz is any jazz that's written after 1960. And so an advanced programmable interrupt controller is anything that's designed after about 1978. Yeah? Which I thought was quite cool. Well, that's my second ACPI joke. Oh, and you can have multiple interrupt controllers, I think, which is that if you have a device which has a local interrupt controller, then it gives you a method where you can go and say, tell me about your interrupt controller, and it returns this format of table, but for that device. So it's kind of, you can have quite a complicated interrupt structure. So this is kind of like contractual obligations. So QMU is my favorite platform, but it's other platforms are available. The reference for PSCI is ARM-trusted firmware, and here's a picture of ARM-trusted firmware with a ring wrap PSCI. And so if you were using the SMC calling convention to access PSCI in an ARM-trusted firmware implementation, this is where you would end up. So this is the reference. It's available as source, BSD license, and actually this is what you were saying, is that it can either be HVC or SMC. So we already covered this point in the previous question, which is that how do you access it either by one of these two alternative trap conventions? So I'm indebted to my colleagues in LEG for providing me with some of this information. So, and actually, this was a quote from Charles, who's just stepped outside, which is, in the latest spec, which is not in the kernel yet, but which is in the spec, which there is enough to boot a server, support some of ARM's latest IP, so more than a gig v2.
Could you just correct that? And not support for 6.1 isn't the kernel, it's just specific certain features from ARM and not.
Okay. Yes.
The core support 6.1 isn't the kernel.
Thank you, yes, okay. The ARM support is not in the kernel is what I should have said, yes. So there are more ARM features which are on their way to the kernel, which are defined in the 6.0 specification. And then there are some features on top of that, for example, related to dynamic voltage and frequency performance management, and something called CPPC, which is Collaborative Processor Performance Control. Now, so in the 6.0 spec, introduces something called low power idle. Now, why I wanted to just mention this, you know that I mentioned that ACPI has tables, it has drivers, and it has registers. And so this is an example of new functionality for ARM systems which uses a register interface. So this is so the access of this is defined as register blocks. There's a definition for that register access, and it's basically a register interface defined through ACPI to program the idle states of your ARM CPUs. And the ACPI term is FFH, the functional fixed hardware interface. It's not the register that lives at 255, which I thought initially. So back to device dynamic voltage and frequency scaling. So in this presentation, I'm just going to point you at the leg wiki, which has a lot of information on these new features which are coming. CPPC it's an abstracted way of defining performance rather than the x86 way of saying having a lot of states for the. Please.
Basically, CPPC instead of.
Do you want to go to a mic?
Yeah, we have a mic. Actually, we have a second mic somewhere.
So CPPC, instead of saying go to a specific speed, a specific voltage, like we're used to on like embedded ARMs, it instead corroborates with the platform, the BMC and the platform. So the BMC says that you've got these ranges of speeds and power states you can go to. And the kernel will say things like, I want to go to about 80%, but I'd accept 60% currently. And then the platform can then work out, depending on what current temperature it's running at, you know, how much voltage it's currently got, whether it can actually achieve those states or not. And it might come back and say, well, I can't give you 80, but I can give you 70, which is within your band of acceptable. And then it will change to that state. So it's, instead of the OS being 100% in control of what speed you go to, then it actually corroborates with the platform more. So it's your states are much more loosely defined. They're like go very fast, go not quite so fast, sort of levels of states.
Awesome. Thank you very much, and explains, well, several times, several orders of magnitude better than I could have done it. It's autonomous. It's abstracted, I guess was what I was going to say. And the gentleman there has obviously, as you said, I'm not going to paraphrase because I would do a worse joke. And then platform communication channel. Whilst do we need the microphone?
That's how you talk to CPPC as well.
Exactly. This. Thank you very much. Right. That's how you talk to CPPC. So I actually wanted to end on what was coming, because if you look at what's in 4.1, it's just the kind of basic support. But just this particular time, if you take a small system with QEMU, with UEFI, with the 4.1 kernel or the LEG kernel or patch set, you can actually build a system that shows everything which you can currently do with that 4.1 feature set, which I thought was quite neat, and which was really my motivation to do this. So obviously, if I or someone else were to do this in 6 months or a year's time, they would probably struggle to show these new features on a basic QEMU implementation. They would need something that was running a reference implementation of PSCI for all these much more extensive features. But it was just kind of a way in to build a system that showed what was available today. We talked about CPPC. So I guess takeaways, and this, as I said, this was a consumer's guide. So this was for people who are maybe interested in looking at this and they haven't looked at it before. So I provided a few links to to some of the specs. There are a few references after this slide, if you get hold of the slide deck. But the takeaways for new users: UEFI is a requirement for ACPI. You can build a simple virtual platform with elementary emulated PSCI. ARM idle management has arrived in the 6.0 spec. Some of the interfaces for dynamic voltage and frequency scaling are still works in progress. And ARM trusted firmware is the reference implementation for PSCI. That's all I have. Thanks for your attention. If you've got any questions, any additional questions, please. There are a lot of people in this room who can answer questions in this area, so please feel free to leverage the room as well as myself. No?
Is the DT block fully created from the ACPI tables today then? Is that what's happening?
No. So the DT blob mentioned in the stub case is it's equivalent to the x86 Linux bootargs structure. So it's only there to carry the command line, tells Linux where to find the EFI tables in memory, and from that it finds the ACPI tables. So we don't convert ACPI to DT. That's not possible in general, and neither is the other way around. Does that answer it?
So you still need the DT block?
So no, you don't. So the thing is, the DT blob is only there to pass the command line, and that's only internal between the EFI stub and the kernel. So your system does not provide a DT. It's just that it was simpler for the kernel to do that internally as part of boot, but it's not something you even see.
Any more questions? Okay, thanks very much. Thank you.